This is Chris here, and Dustin. If there's a hashtag for this meeting, I guess it's just Couchbase, like you see on your screen right in front of you. So yeah, you can raise the ruckus on Twitter as well as here. We're gonna tell you, some new stuff if you haven't, had a chance to corner us personally since the merger. We'll tell you. Basically, the topic of this talk is. From a technical perspective, what does the integration between the CouchDB and the Membase technology look like? So we'll dive into that first at a really high level, and then we'll kind of go back through in a low level, give you some idea of what you can expect in the next few months as things are going. But I guess a lot of you are probably familiar with me from earlier webcasts, so. A little short introduction, and then Dustin can introduce himself. I am an Apache CouchDB committer since 2008 and co-founder of Couchbase. The thing that I'm working on right now is our mobile efforts. So getting Couchbase running on iOS. We've had it running on Android for a while. I'll talk a little tiny bit about that at the end, but that's not the topic of this particular meeting. We're going to just talk more about the big cluster, big server solutions we're working on. But first, Dustin, tell us a little bit about yourself so people know who's sitting here.
Yeah, I'm Dustin. I've been involved in lots of various communities. I was one of the developers on memcached for a long time. I guess I still am one of the developers on memcached. We founded Membase as a way to sort of provide the functionality that people were trying to get out of memcached that it was just not appropriate for. So we built a fast database with memcached interface that provides roughly memcached semantics. So we get into that a bit, so I don't need to get into too many details, but that's basically what I do. I write code, and I'm a co-founder of Membase.
Is that also your GitHub handle?
No, I'm Dustin on GitHub.
Yeah, he's got a bunch of interesting projects on his GitHub, but the most interesting one of which probably we're going to talk about next. So what is Couchbase? From a really high level perspective, we're taking the stuff that Membase is already been good at for a long time, and the stuff that CouchDB has already been good at for a long time, and putting them together and making like a great peanut butter and jelly sandwich. Hopefully that's all you need to know, and now you're totally sold on it. Look at that. It's got blue on the top half and red on the bottom half.
The blue is peanut butter.
It was just a little bit of more serious history or whatever on this slide. We were talking to the Membase folks early on, kind of considering the merger, and it was really what became apparent was that their plans for what's next, what were they going to do in 2011 was kind of like, hey, what did we already have at CouchOne, and vice versa. At CouchOne, we knew we needed to work on getting CouchDB scale up and getting it to be the thing that the big customers would be looking for.
And similarly, I've been inspired by CouchDB for a long time. I've used it for projects for years. I've been doing lots of stuff with it, but the types of solutions that we were providing were kind of on a different spectrum, where people just needed really high-speed access to key value pairs specifically. So we had in our long-term plans basically reproduce a lot of the stuff that we learned from CouchDB, but we're not, able to get to it in quite the short term.
Yep. So here we go. We stack these two layer cakes together, get one layer cake, and we hope that this takes us much less time than inventing it from scratch. So just a little bit of background for people who aren't familiar with CouchDB. This is kind of like the top set of features of CouchDB as far as I'm concerned. So it's got a really robust storage engine. That's the crown jewel of Couches. It's got this append-only storage system, which lets us do things like run on mobile devices because it's always in a consistent state. So even if there's a power outage, you don't have to do like a big stressful fix-up phase after the fact. JSON is also good stuff. Allows you to store whatever you want. JavaScript object notation in the database. Just so if you're coming from the Membase side of things in the audience, you're not completely out in the woods here. So replication is another big feature of CouchDB. We will talk about that in detail later, but it's master-to-master replication, so it's quite different from the relational replication or even the replication within a single cluster that Membase has done. MapReduce, this is a big feature. MapReduce and GeoCouch are both features that are for querying the database. So essentially allows you to query all different kinds of data, no matter how ugly or different it is, between each document. So that is the big feature that you're going to get as a Membase user, is the ability to MapReduce across your cluster. And then, of course, Couch is all based in HTTP, and our very short-term plans don't include adding a whole lot of HTTP to Membase, but in the long term, the goal is to build a big, fast Couch. So HTTP is definitely going to come into play there. So yeah, one other thing to know about Couch if you're coming from the Membase side is the motto of CouchDB for since the beginning has been relax, and that plays out in a lot of ways. One of them is that if you do the rock and roll horns and then you relax your fingers a little bit, then you get it looks like a couch. So who is that guy? That's Derek Perez in the front. I just grabbed his picture off of Twitter, and then the smaller picture is Damien Katz, the creator of CouchDB. So that's the gang sign. You can make it for your friends. So let's see. Let's just talk more. So this covered now if you know what Couch is and you kind of have a handle on, we're mixing Couch and Membase, and that sort of makes sense maybe, hopefully. So now let's just talk about Membase. What is it?
So what is it? Membase is you can kind of think of it as memcached plus the stuff that people were using memcached incorrectly to try to accomplish. So we had a few specific goals that were kind of more about what we wanted out of the product. The first is that we wanted the product. I don't know how to press a button, so I'm slow at this. The first is that we wanted apparently I do, and it's slow. We want the product to be simple, so it's very easy to just grab and start using. If you're familiar with CouchDB, you have puts and gets and things like that. We have the similar functionality with your basic memcached operations, put, set, delete, those sort of things. It's fast is really kind of where we get into more interesting stuff. We have latency guarantees that are, and throughput guarantees that are pretty high. I've run 160,000 ops per second on low-end EC2 hardware. That kind of stuff is really what we're going for. Is how do we keep it fast, and how do we keep it predictable? And then the big part is elasticity. So we came up with a strategy that allows you to take all of your traffic going through a single node, having that node become overloaded, and be able to add another node in production, spill over to it while you're taking traffic, without increasing the demand excessively, and then allow it to just sort of balance across magically and all that sort of stuff. Also, we allow you to shrink nodes. So if you are using something like EC2 and you have traffic spikes and then your traffic comes back down, you can increase your capacity during high volume events and then come back and shrink it back down and save cost when your traffic kind of shrinks.
So yeah, to kind of fill in on that, I was really impressed when I first started looking at the Membase technology, because not only does it do all that elasticity, shrink and grow, it really does do it in a way that doesn't disrupt operations. So and also it's real easy to do. So there's like a web UI that looks a lot like CouchDB's Futon that just hits an AJAX interface on the Membase cluster, and so you can add some nodes, and then you boot up the nodes, and then you tell the cluster those nodes are your nodes, and it sees, okay, I have this much more capacity. I'm going to start spreading the data around, and so you can have like we do this all the time. But the first time I saw it, you have a load generating script just hammering the cluster, and you add a node, and there's all these real time stats that are collected and displayed to the user. So you get you can see what is the average number of what's the average response time in milliseconds, and it's really small and stays small even though there's a lot of stuff going on. You can see that under the covers there's more disk operations happening during a rebalance operation, but you watch that stat go up but it never goes up so high that all of a sudden the cluster performance is worse. So it's pretty cool. I really appreciate the work they've done to make the elasticity not just not just a bullet point, but something that actually works.
So our use cases are a bit different from what you might come from Couch. We've got basically things that have lots and lots and lots of users with little blobs stored for them. So our flagship for a long time has been Zynga and their gigantic games that people are probably playing right now while watching this. So hundreds of millions of active users, and we need to get their data very quickly as the user logs in, figure out what's going on. We also had while we were building that, we were running all of memcached for Heroku. We had thousands of concurrent users on a system doing memcached operations with partitionable memcached and all that other kind of stuff. So we've got a few specific things that people are using it for, like different sort of sectors. So advertising is a pretty big one because they have specific windows that they are allowed to ask to make decisions within. So in some of these cases, actually one we hear quite a bit is 40 milliseconds. A request comes in. If they can't come up with an answer within 40 milliseconds, they have to just abort and let the request through because they can't slow down the web request at all.
So this is this is one of those fun times when the the latency of the system directly corresponds to how much money they can make. So basically they've got 40 milliseconds to find the highest bidder, and if it's 30 milliseconds have gone by, they may have to just drop back to a bidder who's not the highest bidder. But if they, if the system's all working and tuned properly, then they should be able to get the most revenue. So this is one of those things where if Membase only takes up 1 millisecond, then they have much more time in order to do their actual, math and all that.
And we do try hard not to take a millisecond.
Yeah, these guys say a millisecond is a long time. To me, it sounds fast.
Yeah. So we've also got gaming is a pretty big one. We're big in Korea. One of the founders is a Korean company that is described to me a lot as the Google of Korea. I'm not very familiar with the Korean market, but they have a lot of machines, and I get to hear about some of the stuff they do. And they sent a few developers over for a while, and I worked closely with them. They're a lot of really smart people, and they basically have the equivalent of Google and Twitter and Zynga and all these sort of things inside of South Korea. And I figure since they have gigabit Ethernet to their house, they're probably doing a lot of stuff there.
So now we're going to talk about, what is this technically, how ambitious is this thing we're doing the next couple months, and what's the big, overall shape of it, so you can know what to expect. How soon will it be before, if you're a Couch fan, that you can get some of the features you like with the big scale, low latency that Membase offers, or if you're a Membase user, what about Couch are you going to get? So yeah, neither of Membase or Couch are SQL, so the combined product is definitely going to be NoSQL.
Well, I don't know. We actually do contain SQL, but nobody knows that. But the main thing that we have right now is all of our data that comes in is handled in this in-memory structure, and then we write it out to the file system as quickly as possible. We're currently using SQLite as a file format. It's a really awesome file format. It's indestructible. If you haven't read their testing page, it's just one of the most inspirational things for software developers. But what we're attempting to do, attempting makes it sound like I haven't actually seen a lot of the stuff work. But what we've been doing is taking the layer that's on disk as SQLite today and replacing it with Couch. So there's a few things that are happening around that. One of them is we're working a lot on making CouchDB fast. So CouchDB has a reputation of being not really, really high performance. It scales quite horizontally. It's got fairly predictable performance. It scales both for across machines, but also on a machine pretty well. But it's not fast coming from memcached perspective fast. So the main thing that we've been doing to fix that is to tell Damien to fix that. And setting that as a priority, he's been doing some really nice stuff, as well as Philippe, who's sitting in this little box over here on the left. The other parts involve taking our persistent store and replacing it with Couch, such that all of the specific document operations are basically handled in memory. So if you have a document put, we can respond to that roughly instantly. Gets typically as well, and then the things that end up getting stored on disk, we can go back and request as part of views as they materialize. So we have, from this perspective, we basically have Membase and Couch as a backing store with some of the Couch features for MapReduce and stuff like that.
Yeah, so I've seen some questions going by in the sidebar. There's some stuff about how schemaless is Couch. We can come back to that. There's another question about what in this picture is Erlang. Well, first of all, I should say, yeah, something is up with, I guess, the PDF export. I'm looking at it on another screen, just off the raw PDF, and it looks okay. So maybe it's an interaction between Adobe's presentation software and their file format. So anyway, what you see on the top there, there's that dotted line down the middle. Everything above that line is, quote unquote, yours, and everything below that line is the stuff that we do. So, your application is going to include some kind of Couchbase library SDK thing, which will then talk to the server over both the memcached protocol and the Couch protocol. So for today, if you go use Membase, it's all memcached protocol, and that's great because it's a persistent socket connection, and you can pipeline a bunch of stuff over a connection and get these low latencies and not have to worry about negotiating new connections all the time. And then Membase, the bottom part that's also a little bit jumbled, is basically memcached sitting on top of what we call the eventually persistent engine. So that engine is in charge of saying, hey, what bits of memcached data need to go to disk? What's dirty? What is effectively just a cache of what's already on disk? That engine also handles doing the between box replication, so that if you need to keep 3 redundant copies of your data, that happens in the EP engine as well. So currently today, that's all getting shoved into SQLite. This is so our first step is replace SQLite with CouchDB, and with a with CouchDB that will hopefully be magically faster than the CouchDB we have today. And it looks like it will. I don't want to say exact numbers, but be on the lookout for commits from Damien into the Apache project that are screaming fast. So that's going to be nice, but still not nearly as fast as memcached is alone. So.
Well, and that's we have specific targets. The things that we've been doing with SQLite, we've pretty much hit the limits of what can be done with it. We've done all of it, and we've had Richard Hipp sitting in the room with us, so we have on good authority that we're doing kind of the right stuff. But we have that does mean that we have specific targets. So I get to hand Damien an application and say, make faster than this, and we can know for certain that we've not only been able to catch up, but potentially exceed that, and then under various conditions where SQLite starts to degrade, that we can avoid degradation.
Yeah, let me tell you, I haven't seen Damien this happy in months, because he's getting to just sit there and make Couch faster. So yeah, the other question that came up that I think is now's a perfectly fine time to answer it is about Erlang. So Membase has big parts of, actually, we might even have a slide coming up on this, but just to answer, Membase has a lot of parts of it written in Erlang. The actual critical write path currently, which goes, memcached, EP engine, SQLite, doesn't touch Erlang, but the cluster management does. So now we're going to have Erlang-based storage engine, but it's not it's not a huge change, but there's a bunch of people, in this office with me who are good at Erlang, and so that was another reason why the merger itself was appealing. It looks like I jumped a slide.
I think you.
Oh, maybe I must have pulled that out.
Yeah, I think you must have introduced a new thing.
Yeah. So let's see. There's one question that might come up is is how are we going to store memcached stuff in in CouchDB? So we don't have a slide for this, and I won't try and back up just so that we're on the slide that's also not for this. So this robust storage engine, your screen says that, but we're talking about the way that we're storing memcached stuff in Couch. So basically, there is kind of a wrapper that Dustin and some other people have come up with about how a memcached set turns into a couch put and vice versa. But that will allow you to store JSON in Couchbase as well as other stuff. So if you are already used to storing raw HTML directly in memcached, you'll be able to swap out that memcached for Couchbase, and now you can query over those raw strings that you've been storing.
Yeah, the way to sort of think of this is whatever data you store in Membase, you will be able to retrieve from Membase exactly as you stored it. But we do have, and from that you can do MapReduce over keys and some basic metadata, but not necessarily values, because we'll be storing the values as attachments. You'll have a giant blob of JPEG or whatever it is you're storing. If you turn on the Hey, I understand documents feature, then you can store JSON documents, and we'll actually make them proper couch documents as they flow through the system. And from that, you can do MapReduce with understanding the full value of your document and do all kinds of wonderful things. And that also allows you to do a mix of JPEGs and JSON documents and HTML or whatever other types of things that you might want to store, and we'll just do the right thing. And this code all works today. It basically says we have specific rules about how we understand the JSON document. So there's you can't have fields with underscores or $signs on the top level. You can't. It has to be properly formed JSON. If it's incorrect, it will just store it as an attachment and give you back exactly what you put in. But if you store your JSON correctly, then you can use it in views, and you can do all kinds of fun stuff with it.
So now we're going to drop into, so if you're like already know everything about CouchDB, this may not be big surprises for you, but if you're still learning about Couch, or you want to know what kind of Couch features Membase is going to get as we do this integration, now we're going to kind of barrel through some of these Couch features. So what we said is we're essentially swapping out SQLite as the Membase storage engine for CouchDB, and that's what makes it Couchbase. So let's talk about the CouchDB storage engine. It's append only, which means that every time there's an operation against the database, we just add bytes to the end of the file. So no database operations can corrupt the file, because we're never going to go in and mess with something that was already committed. That gives you a whole lot of peace of mind as an end user. One of the important features is that if there is an uncontrolled shutdown, when you go to reboot it, there isn't any kind of consistency check or fix-up phase. You're already safe, and so this makes working on a cluster it's just easier to reason about. So if you have if one of your boxes gets overloaded or something, you can just shut it down and bring it back up, and that's often the best way to check to see if you can fix the problem quickly. This also allows us to serve concurrent readers really easily, because you can have, as you can imagine, writers are never going to be interrupting readers, because a reader grabs the file as of when they started, and they're only interested in stuff that was already on disk at the time their read began. The writers can proceed to just lay down more data after that point, and it'll never interrupt the reader.
So MVCC is sort of a side effect of this type of design.
So that's, and then you can also do hot backups off the files, so it kind of helps operationally. The one thing,
you can copy a file that's being written to non-atomically and end up with a correct backup.
Yeah, you can just go do an rsync or SCP or whatever to pull one of those files off a box, and then it'll be a little bit out of date by the time the copy is done. If your main server was under a load, but then you can use replication to bring it up to date. The only downside, right? It sounds like, oh, silver bullet, everything should be append only, but of course you have this file that's always growing forever unless you do something about it, and so that is what compaction does, and so that's kind of an administrative process you've got to kick off. Ideally,
it's an administrative process in existing CouchDB, but part of the work that we're doing is to make it not be an administrative process for the most part. So we're actually, Philippe is in here right now in another window writing code to start tracking better data on manipulation to determine when a compaction would be necessary. So when we've decided that we've changed too much data and compaction would be important to shrink, then we can start doing that as it's running.
So yeah, that's the basics of the storage agent. Oh, there was a question. I pressed the button earlier. I saw a question about what's that a picture of in that last slide? That's a picture of the timekeeping mechanism from the clock of the long now. It's designed to keep accurate time for 10,000 years. So I thought that was a good picture for reliable storage. So this BBC graph is, I won't even go too much into the details, but they gave Couch a big workout before they chose it as their storage system for their next generation architecture, which is now getting rolled out to handle more and more of their traffic. Essentially, what you need to know from this is that they threw data at Couch for 2 days, and they could see that it was able to absorb these big workloads and not slow down and not have kind of unpredictability. And for them, predictability matters most. So
the one thing that you should note from this is that you see there are actually this one is labeled. So there's alternative data stores that they tried that started out ridiculously fast, and then you hit a wall very soon and the performance drops off, whereas the Couch performance just kind of linearly slows its way down. So there is a point on a given node where performance is undesirable, but that's within an hour or so of what they were competing against.
Yeah. So the overall thing, they knew they were getting into this data storage for the long term, and they wanted to know that they had a storage engine that could handle their long-term needs, and also that whole fast crash recovery really matters when you're overloaded. If you're overloaded on a traditional storage engine that doesn't, that's not always in a consistent state. So let's say you've got your relational server and it just gets pushed into swap, and all of a sudden everything is 1,000 times slower than it used to be. One of the things you're not allowed to do at that point is just kill-9 the server and boot it back up. I mean, you could, but now you may be sitting on a whole weekend while it's doing a fix-up phase and your site is down. Whereas with Couch, if you get locked up somehow like that, you could just hit kill-9 and bring it back up right away.
Crash only is the term there. There's not a safe shutdown for CouchDB because it's unnecessary.
Yeah. So and if you think about it, this is what got or recovery-oriented computing is another way to talk about it. But if you think about server processes, how often would you ever shut down a server on purpose? The whole point is that you boot it and run it until the end of time. So why do they have special code for shutdown? So chances are, the more long-running a process is, the higher proportion of its of the ways that it shuts down are going to be uncontrolled. So build your processes with that in mind from the beginning.
Oh, hey, look.
Yep. Okay, so this is and that slide got all messed up. So this slide came from PowerPoint into Keynote, and I'm going to just say that's why.
Well, from OmniGraffle first.
Yeah. So that was the JSON stuff we talked about encoding memcached operations as JSON documents.
It's what the documents look like. If you were building a MapReduce right now against code that I have right now, you would need to know this right now.
So it's going to be some variation on this when you're actually using it. And the APIs, again, this is going to be just super duper simple. Set a key, set a value. We're working on some other set a key, get a key.
Well, this is the effect of having done that. So what we have is this concept of JSON document mode where we intend to understand the JSON documents. So this is just demonstrating that If you're in basic Membase mode, if you store a value, you will retrieve the value, and it will be an attachment. And if you're in JSON document mode, on this first example where you're not storing a JSON document, then it will work exactly the same way. And then if you're in Membase mode, you store a JSON document, it will store a JSON document as an attachment. And if you're in JSON document mode, it will do the right thing. Basically, this says if you turn on the feature and you use the feature correctly, it will do what you want. Otherwise, you'll get back exactly the same data that you put in.
So it looks like we're building up a lot of questions about the cluster support. Maybe I think maybe we should just kind of go in and answer a few of those real quick because we're going to start getting into the programming model, which isn't quite the same as the the cluster model. Coming down from the side, I would say two questions asking for comparisons against other NoSQL databases. The thing that Membase really shines at is ultra low latency under giant scale. So, Zynga, AOL, all these customers, really lean on the fact that Membase can turn around a response in less than a millisecond, sometimes a lot less than a millisecond, and I don't think that any of these other databases are fast at that level. Some of them, can get close, but like an order of magnitude close.
We also have a different consistency model than a lot of these. We don't do eventual consistent kind of clustering stuff. What we do is we say we have a more simplified application development model where if you put something in the database, that's what you will get back, barring any sort of disaster. I mean, you always have the backup kind of problem, but if you put something in, you will get it back. If that's so that does require that there's an ownership for a particular segment of the store, and if that segment is dead, then you bring up your replicas and all that sort of stuff. But we don't have the ability to say just throw it in any given server and we'll work it out later, which is actually a CouchDB feature. And we're mixing and matching that so that you can choose which type of management you want in the future. But where we've been really strong in Membase is there's one owner for any given piece of data. That owner will replicate it, persist it, and do all this other sort of stuff. You can move the owner at any given point, and you can do it under heavy load, but it's always one place, and you'll always get the same thing that you store.
So yeah, what Membase itself is a strong, consistent store, so that when you're working, when you're browsing a Zynga game or something like that, you want to see that your farm hasn't changed in unexpected ways or reverted to a previous version of itself or something. So that strong consistency is really important for those models. What we're gonna in the long run we'll be blending, like Dustin said, the replication models, and so within a given data center you would have strong consistency, but then across East Coast and West Coast you may have eventual consistency using the CouchDB replication model. So I guess I guess that may cover some of the advantages against other NoSQL databases. The other stuff we're going to get into. So if you're not familiar with Couch has a really rich programming model, especially for real-time queries, and that's that's sort of more powerful than some of these other ones. So if you've just been using Git or set and Git in Membase, now you're going to be in for a whole world of capabilities. So yeah, so incremental MapReduce. This is one of the, imagine that layer cake picture from early on, and we slap Couch on the back end and nothing changes, except this one thing is that now you can query it. So there's tons of memcached clusters out there where no one knows what's in them. And Membase, it's only a little bit easier to get a bird's eye view of what's in a Membase cluster. But now with Couchbase, you'll be able to write a query that runs across the entire cluster and tells you, what is the most popular, item in your game, or, what are, who are the busiest players, and, outside of the gaming world, you can do transactional queries. So, what is my bank account balance now? That sort of stuff. So this incremental MapReduce is pretty serious query engine. Lets you do all kinds of stuff. the big sweet spot for it is interactive data workloads. So, online transaction processing, the stuff that we're used to on the web, over data that may be heterogeneous. So maybe an old version of your application used to save, the user preferences in one format, and a new version has changed the format a little bit. And the MapReduce view could go through and normalize between those two formats so that the display logic only has to deal with the new one. So those kinds of queries are what it's good at, and soft real time and incremental. So if you're familiar with like Hadoop MapReduce, that's a batch process. That's give me all the data in the world and run this function on it, give me the output. With Couch, it's like that the first time, but then the output can be kept up to date incrementally as the input changes. So when you define the query, you have to build that index, and that takes time. Part of our job is to make it not take much time, but still, it has to traverse the entire collection.
It's the difference between grep on a log file and then grep on the log file again, and then piping the tail of the log file through grep and maybe suspending it periodically and restarting it. So only the new stuff that's come in is what you're interested in updating, and that's what you fetch. The interesting thing is, to me, is that the model of MapReduce that's done here is very similar to what you do in relational databases. The primary difference is that when you're doing things in relational databases, you sort of have to think up front of everything that you're going to be doing, and then do your data model around that, and then have your application bend around that, and your application has some object with a whole bunch of stuff for a user, and you spread that out into all the different places that you'll be storing stuff. Whereas in like a CouchDB, you have the data that you have, you store the data that you have, and then you come back later and you decide how you want to look at the data. So you can sort of imagine it as late schema design instead of early schema design, or I like to call it duck tables.
Okay, so I saw another question on the sidebar about the cluster capabilities. Yeah, one of the things that Membase is real good at, does today in production for, high volume users with hundreds or maybe even thousands of nodes in a cluster, is when a node goes down, it's really trivial. A single command, or you could write a script that's watching for that and does it for you to promote the replica to take over, so that you can heal the system and keep going with no downtime. So yeah, you're gonna, if there's things that you think of, hey, this might be important because I want my data to be online all the time, and I want to have, I want my users to be able to trust my web service. So yeah, I need my database to be fast and available all the time. That's what we've been building. That's what Membase has been building for a long time and is good at. So answers to the questions of, what does it do in such and such a situation? Probably the decent answer that you're looking for, and not the answer that sounds like we made a big mistake somewhere. So back into the MapReduce query. What does one of these look like? So this is a quote unquote join. This in the white box. The black stuff is a reduce, and we'll come back to that. But just if you look at the white box, this is how you would define a single query to find a blog post and all of its comments. So what this does is it's passed each document in the database in turn, and so then it can inspect that document. So this is all just JavaScript. It was handed a JSON object essentially, and it says, hey, if this JSON has a field on it, a top level field called type that has the value post, well, now we're going to do one set of logic. But otherwise, if the type is comment, we're going to do different logic. So the logic here, and this goes into the guts of how the MapReduce is actually built. We're just sorting stuff. So what we want is to sort posts by their ID, and we want to sort comments by their post ID.
It's not just sorting, but it's also sort of rewriting the data that's in the database. So in this example, you're both sorting it by doc ID, which allows you to fetch by doc ID. So when you're issuing a query against this, you can say, give me everything that starts with this doc ID. But then also, the content that you get from this is the first document being the original post, and then all remaining documents being comments for the post that you'll attach to it in the same form.
Yeah. So this is you can do all kinds of stuff like that. Then the reduced side, you can really shoot yourself in the foot with reduced if you try. But well, I just say I recommend, and this is this webinar is not the documentation. Go look at the documentation. But there are 3 built-in reduces: underscore count, underscore sum, and underscore stats. And if I used to go write crazy reduces and like try and come up with something really clever. And as I've gotten to be more proficient and kind of more comfortable working in Couch, I don't do that as much anymore. I write my map specific for the reduce I care about, and then I just use underscore sum or underscore count, and you're going to get kind of a less headache experience doing it that way. So hopefully this reduce isn't too scary, and if you're looking close, you can you've also learned how to do a join in the Couch view system.
Yeah, that was kind of neat. I haven't seen that one before.
So who's using this MapReduce already? CERN has a case study on our website where they talk about, this MapReduce is so easy, even the intern was able to browse physics data in real time with the magic powers of MapReduce. CloudSplit is a startup that is kind of giving people a real-time view of their EC2 spend. This is just the tip of the iceberg. I wanted to put the CERN one up there really big because that's a pretty picture. So a little bit about how it works on disk, and this one's really hard to. I'll try and do this slide without you being able to see my hand waving. But the key to understanding how the reduce can be fast is to understand that along the bottom row, the bottom layer of that tree, that's the actual emitted map keys. So we've got things sorted by alphabet there. Then if you think that, let's pretend that the reduce function we're using now is the underscore count reduce function. In each of those inner nodes, it's going to store a, the count of what's below it. So in this particular illustration, you'd have the number 3 stuck in each of those 3 nodes in the middle layer, and then the number 9 is stored in the top node. So if you were to add now a new a new key, B and a half in between B and C there, all that would need to be updated by the database as far as cached values is the number 3 in the red box will be turned into a number 4, and then the number 9 will be turned to a number 10. So what that means in practice is that you can keep these reductions up to date in real time with logarithmic cost. So it's when you're wondering how is Couch able to do all this stuff in real time, it's because it's using every piece of the B tree to get something done. Some interesting questions in the sidebar there. So the question about backups. The best way to keep backups is with replication, and then your backup can be not just a backup but live failover.
Well, we also have in Membase we have ridiculous backup types of tools. So we have if you're familiar with the changes feed from CouchDB, we have a similar concept, but we sort of segment it in chunks that provide sort of barriers across these things. So you can take a you can take a backshot as sort of a point in time, and then you can take another one at some point later that will contain a few of these checkpoints and be able to discuss the checkpoints across all these sort of things. The end result of that is you can take some arbitrary number of backups and then play them incrementally in reverse order from any given point in time. This is something that Zynga uses a lot for doing recovery, because they run a lot on EC2, which means that they don't run a lot on EC2. So they have to go back and do online recovery. So they'll take one of their hourly backups and then a few incrementals on top of that, and then run those backwards and get the system up and running live. So we've got, I think that one of the most effort requiring features that we put into our next release is just ridiculous backup management. Anything you could ever imagine wanting to do, we put into it. I hope, because we had a lot of imagination sitting around thinking of it.
So we've just kind of discussed that last slide, the incremental MapReduce on a single node. How does it look on disk? How does this going to work on a cluster is it was also one of those things that it's the architecture of both Membase and CouchDB was well suited for it. You wanna...
Yeah, I mean it's pretty much the same type of tree traversal, except we have split the tree into multiple different segments across multiple different servers, and then we take those segments and run them all in parallel, and then sort the results and bring the sort back as a merge that's emitting all that sort of stuff.
So it's no different in architecture really from what's happening in either CouchDB Lounge or Big Couch. It's just scatter gather. Make sure that the indexes exist on all the leaf nodes, and then pull back the results. And it's a constant space merge sort. So
and that's what we're doing for and that's just fitting into the Membase type of management, because we already build these types of management trees, and we already have the communication across the cluster and all that other sort of stuff. So all we're doing is feeding the data through. We've done lots and lots of different types of models of just use cases really. So we can say you've got all these documents like the previous one that has blog posts and comments, and then like what if we had Blogger running inside of the Couchbase cluster, and then we have a ton of concurrent requests coming through for lots of blogs and their comments. How would we fit this all in a single request? Or what if you just wanted to do something like give me all of everything all the time? Can this actually scale across a cluster? Can we run? Can we pull all data out ordered across all nodes on a 1,000 node cluster? And the answer is approximately yes. We do have issues where we expect nodes to fail during that, so we've got accommodations for that, but that's what we're designing against.
So just like a MapReduce can be scattered, gathered across the cluster, the GeoCouch support that we have will also be scatter gatherable across the cluster. So you'll run the same geo indexes will be local to each cluster member, and then you can pull up stuff in a geographic region and aggregate it until you get the full set. So using that same scatter-gather architecture. Replication now, the peer-based replication that Couch is so famous for. This is going to be review for anyone who's a big Couch user, but this is the neat one of the neat things that Membase is getting is the ability to do multi-master replication. So I'm going to kind of tear through this a little quickly. But
there was a question about doing replication across clusters, and this is where this strategy comes in. So inside a given cluster, we're using Membase replication, which is guaranteed consistent and using a different protocol and all very tightly controlled as to who's writing and stuff like that. Across clusters, we're going to be using couch type replication. It may not be exactly the same protocol, but we do plan to support the exact same protocol. So that will give you the ability to introduce inconsistencies, because you'll be able to do master-master across regions, but this is how it works.
Yeah. So operationally, you just post some JSON at a couch and tell it the source and the target databases, and it makes them the same. And so it'll push all the updates from the source into the target. You can trigger, the both corresponding replications at the same time, and you'll get bidirectional replication. The sources can both be remote, so if your firewalls are laid out where the two sources can't reach each other, but some third party can reach both of them, that third party can do the replicating between them. A lot of flexibility. Then there's the universe that we all hope to see, where there's a couch in every copy machine, Toyota Prius and cell phone. And so it's going to take us a while to get there, but we're on the cell phones now at least. And so this is going to require some features that are on our long-term plan for replication management, so that if you're somebody like Zynga and you have millions of users, but you have one user who has some very, very small proportion of the total of your data set, and they want to be able to take their data, that small proportion, offline. We're in our longer-term roadmap working on some tool chains to support taking a subset of the data and replicating it down to a mobile device.
And these are Couch features that exist today for the most part. You can take bidirectional replication across servers and then have a sort of foreign replicate that is a subset of the data based on whatever computation you want to throw at it. So I've got an example where I've got a photo album that I often build on my laptop, or I have this machine running somewhere that's hooked up with Dropbox and takes photos that I put into Dropbox and grabs all the data out of them and stores them, and then replicates it to ISIS Couch, and then maybe to my laptop if it's online at the time. Otherwise, my laptop will pick up from either the cloud or my home machine. But one of the ones on ISIS Couch has a replicate that is a subset of the data that's publicly available. So I can choose to decide that this section is meant for everybody versus this section that's meant for these users, and split that out.
Yeah, so all that is doable in Couch. You just kind of have to read all the docs, and we want to make it drag and drop easy, I think, or something, something as easy as that. So this little slide here should be of interest to anyone who's got kind of a long-term, they've been using Couch for a while, because we all know Couch started in 2005 when Damien started coding on it, and it also kind of brings this what seems new replication model, this master-master replication model, at least for the web, right? It brings this capability to the web. So I recently found this paper, Optimistic Replication, which was actually written around the time that Damien was getting started on Couch. And so it doesn't describe Couch, but it may as well be. It describes a bunch of similar replication capabilities, and that's that have been going on for 20 years. So this was good for me to see that we didn't just invent something brand new, some crazy Couch stuff. This has been around for a while. So I saw a question down there in the corner about mobile and iOS Couchbase. That's what we're going to end on. I know we've only got a couple minutes left, so I just want to talk about how this all fits for mobile. That GitHub URL at the bottom of the slide now, that's what you want to go to see the latest iOS Couchbase. And I actually have some pull requests that I'm working on getting in there, so the build is getting cleaner. But it works. There's a demo app that runs in the simulator and on the device. We had to do a bunch of stuff to get Couch to run on iOS. I won't go into that here, but I will just talk about, hey, what's good about mobile and Couch. So we already talked about the robust storage engine, but that really matters when your battery might pop out of your phone, because the last thing you want to do is when you stick the battery back in, your phone kind of like goes into lockdown and says, I've got to fix up my storage engine. That's not what you want. You just want to use it. So Couch is a good fit there. We also found when we put Couch on Android the first time that we couldn't measure any impact on battery life, so that was a good sign. It's the download is still a little too big. It's about 15 megabytes of additional space it adds to your App Store apps, but we think we can crush that down to 5, maybe even smaller. And at 15 megabytes, that's even that's okay if synchronization is really important to you. And at 5 megabytes, it's okay if synchronization is somewhat important to you. So that's what we're targeting there. Pure-based replication, I don't have to dwell on that anymore, except for, hey, that's why it's obviously neat to have the data right there on your phone. Yeah, so a good question. How does Couch know when to try to replicate or not? If you configure a continuous replication, it'll just keep trying. It'll have exponential backoff if it can't reach the target. But basically, it'll just keep trying. At the more macro level, who to replicate with and when to trigger those replications, that's an application concern. So geospatial, also great on mobile, right? Because you're out there in the world, you want to see what's near you. HTML5 application server, this is more pertinent on the mobile than it is on the giant cluster right now. But if you wanted to deploy an app to the cloud and your device, you could just put it in a PhoneGap container and have Couch serve up the same HTML5 interface on the device and from the cloud. So that's an option.
Couch apps are pretty awesome.
Then there's, here's a few of our mobile users. I can't go into too much detail because of time constraints, but this Rapid Family Tracing Reunification project in the upper left there is really neat. It's a UNICEF project for reuniting families and children after disaster strikes. So you go into Haiti after the earthquake. They didn't have much internet before the earthquake. They certainly don't have much afterward. Set up a Red Cross tent and a Wi-Fi zone, and people go around with smartphones, take pictures of kids, take down descriptions of their parents. Where'd you last see them? Over on the other side of town, talking to parents. Where's your kid at school? Those kinds of questions. And then instead of having a big mound of paper, they've got to shuffle. In an emergency.
And replicate.
Yeah.
They have data that spreads like a virus.
Right. So now everyone has all the data on their smartphone, and the idea being get these kids, back in touch with their parents before the kidnappers swoop in. So I thought that was a pretty cool use case. So yeah, I think that's. Oh yeah, good question about Android down in the corner. We've been on Android since almost this time last year. So there's the Android was just way easier to support. It was starting to get out ahead too far. We realized that the constraints on iOS were so deep that we wanted to, if we wanted to feel native on iOS, we should do that first, and then take whatever kinds of constraints an application model falls out of the iOS world and translate that to the other platforms. But if you just want to get in there and run Couch on the Android, it's been on Android for a while. Whatever the latest Android release is, threw us for a loop on a couple things, so we're working on a new build for that. That might even be up by now. I know Dale was working on it on Sunday. So this picture here, this is going to be the last slide I think we actually talk about. But over on the side there, Demaji is really cool use of replication. It's a network of health clinics in Africa where they may not be online. They're out in rural villages and there's no landlines and there's cell coverage, but maybe it's got 10% uptime. So they replicate during that 10% and do all their operations locally otherwise, and it gives the clinics an ability to have an online, fast web experience, and also to communicate with headquarters and send, public health data back and forth. So basically bringing internet to communities that aren't wired up for, network connectivity. Ubuntu One, a big user. They have millions of databases in their cloud. They have a relatively modest cluster with, hundreds of thousands of paying users and millions of databases all replicating between, millions of desktops and phones and everything. So they're really taking this kind of vision and making it real. So that's it for what we want to talk about. I'm happy to sit here and answer questions. I'm not sure if we've used up our whole time slot, or people want to hang around. But thank you for coming out.
Hey, Chris and Dustin, thank you. What a great webcast. I'm always amazed by how well you guys speak and answer all the questions while doing so. So I just want to say thank you for doing that, and I'm happy to keep this room open for a while if people have questions, or just let me know what works for you guys.
Sure. Well, I see a couple of questions built up in the sidebar there. There was one about Lua. There's no official Couch plan to add Lua support, but adding new query languages is like super easy. So we've already got Python and Ruby and Java. If you wanted to add Lua, that's probably a weekend hack for the right person.
Yeah, it's part of your view definition. When you specify this is my MapReduce job, you also specify the language, and then whatever language is support on there. So Iris Couch will, if you're a happy paying customer, I'm certain it will add language support for your hosting services. Built in, there's JavaScript and Erlang, and JavaScript is pretty decent, but it's not the fastest runtime out there. The Erlang stuff is pretty awesome.
Yeah. Yep. Good.
Yeah, whoever this is who's talking about Perl as a query language, I don't support that.
Yeah. Lua is lightweight. I mean, if what you really want is lightweight query language, write your queries in Erlang. I don't care whether or not it's got a faster runtime than whatever language you wanted to use. You won't have to do any inter-process communication, and that'll make up for whatever other speed boost you thought you could get by using something other than Erlang.
I can't respond to Ken's question for various reasons.
Yeah, so I mean, I can answer Ken's question. The Twitter firehose isn't that big. That's my answer.
Yeah, it's what a word every 750 milliseconds right now. That's pretty boring. Oh, no, 750 a millisecond. Yeah, that's still boring. 10-node cluster would be bored doing that, in theory.
Yeah, it depends on what you want to do with that fire hose. All right, so I guess we are. I guess we're wrapping up here. So the video will be on O'Reilly's website and on YouTube. It usually takes about a week for those to get posted, and that's. I think we'll just stick to that. I could throw the slides up now, but the slides are kind of a jumble without the talking to go along with it. So thanks everybody. Feel free to harass us on Twitter. If you use the word Couchbase on Twitter, we're gonna see it, right? Like there's not
Can't hide.
that size of the fire hose is small enough for us to personally absorb. We don't even need a cluster. So yeah, thanks again for coming out, and
Hey,
look
Chris,
forward to hearing from you in the future. Yeah.
what's the date of our next webcast? I'm sorry, I should know this, but we have one next month.
Yeah, we have one, I think, on the 20th of May, which is going to be about Couchbase mobile. And then, Catherine, I also emailed you if we could do one. I would like to do a hands-on hackathon for jQuery users before the end of the month, but maybe we'll talk about that and nail down the date.
Before the end of this month?
I thought you had maybe a date available. If you don't, we'll figure that out offline. But
we can probably make it happen. So just let me know.
Yeah.
Okay.
I saw something about maybe the 27th. I don't want to pin anybody down to anything here, but I will say if you're a jQuery user, keep an eye out because I want to do sometime maybe in the next week or two a little hands-on live code tutorial jQuery CouchDB that will be by far the simplest of any of those hands-on tutorials that I've done before. I had a good experience on Sunday at the jQuery conference giving that. So.
Okay. All right, great. All right, well, thank you guys, and thank you everyone who turned up today. Always have a great group for this.
Yeah, thanks, Catherine. This is always fun.
All right, so I'm going to, let's see, we're still getting questions. I think I'll just count to 10 and...
Some of them are serious.
Yeah. Yeah, System 3, you've had lots of questions pouring through there. I haven't been able to answer all of them, so hit us on Twitter, or anybody can also email jchris@couchbase.com.
Or Dustin.
And we'll make sure that we at least point you to the right documentation.